All right, a ball of mass 0.1 kg approaching a tennis player with a velocity of 10 meters per second is hit back in the opposite direction with a velocity of 15 meters per second. If the time of impact between the racket and the ball is 0.1 second, calculate the magnitude of the force with which the ball is hit. All right, so what do we have? We have the mass of the ball. The mass of the ball is 0.1 kg. We have the initial velocity u, 10 meters per second. We have the final velocity v, negative 15 meters per second, right? And it's negative because it's going in the opposite direction. We have the force, we're looking for that, and then we also have time, right? The duration of the impact at 0.01 second. All right, so we can use the formula that equates impulse, because impulse is equal to change in momentum. All right, and our formula for impulse is Ft. So F times T is equal to change in momentum. Change in momentum, that's final momentum, which is mass times final velocity, minus initial momentum, which is mass times initial velocity. Right, so if we plug in, we have F times 0.01 is equal to mass 0.1 times final velocity minus 15 minus mass 0.1 times initial velocity 10. So F would be, or let me say 0.01 F. So 0.01 F would be equal to 0.01 F would be equal to negative 1.5 minus 1, right? When you do that, so we'll have F be negative 2.5 over 0.01. F would be negative 215 newtons. All right, so the answer is C. The answer is C. Now, the reason why it's positive 215 that we're taking, because they asked for just the magnitude. Remember that force is a vector, and the reason why the force is actually negative is because the force is in the opposite direction to the initial velocity that we called positive, right? So we call the initial direction of the ball positive, and the force is in the opposite direction. That's the reason why we have our F as negative 250. Now, you could have also wanted to go the route of just do F is equal to ma. Right? You could have just done that. F is equal to ma. And then we can calculate our A from equations of motion. I think we should be able to use V is equal to U plus AT to calculate A, and then substitute in. So let's plug that in. V is minus 15. Minus 15 is equal to 10 plus A times 0.01. So if I move this 10 over, sorry, times 0.1, sorry. Sorry, okay, yeah, times 0.0. Okay, so we're good. So this will be minus 25 is equal to A times 0.01. If I divide both sides by 0.01, that will make A to be 2500, right? So 2500 meters per second squared. So that I can come here now and plug in, right? So just use your F is equal to ma formula. That will be F is equal to 0.1, which is the mass, times 2500, actually minus 2500. So F would be equal to 250 minus 250 in newtons. So either way you get the same answer. Either way you get the same answer. So what's the idea is that you should know as many of the relationships as you can, because they are all, sometimes you could have a question, and even though you don't know the exact formula you're supposed to use, you might be able to find your way around it. So the more formulas you know, the better for you in physics. All right. So question 2 says, a ball of mass 5 kg hits a smooth vertical wall normally with a speed of 2 meters per second, and then it rebounds with the same speed. A ball of mass 5 kg hits a smooth vertical wall normally with a speed of 2 meters per second and then rebounds with the same speed. Determine the impulse experienced by the ball. Okay, so we're going to use a formula that says that impulse is equal to change in velocity, change in momentum rather, change in momentum. Okay, so impulse will be equal to change in momentum will be mv minus mu. So let's drag out our variables. We have our mass as 5.0 kg. All right, we have our initial velocity. Let's call that 2.0 meters per second. We have our final velocity. So your final velocity will be negative 2.0 meters per second because it's in the opposite direction. All right, so we have all we need. So that means this is going to be 5 times minus 2 minus 5 times 2. That'll be minus 10 minus 10, which gives you minus 20. All right, so that'll be minus 20 kg meter per second. All right, so the correct answer is C. Now, the idea behind the signs is it just depends on what you deem as positive direction, right? So if you had taken the other one, the initial direction as negative, then you would have, when you did the calculation, you would have gotten the positive. So the sign shouldn't really trip you, right? It just helps with understanding the change in direction for everything. So the correct answer is C. Okay. Question 3. A ball of mass 5 kg hits a smooth vertical wall with a speed of 2 meters per second and rebounds with the same speed. Determine the impulse experienced by the ball. Okay, so it's the same question we just solved in the previous like the very last, so the question repeated, right? So you can just go back a bit. Okay. A body of mass 2 kg is suspended from the ceiling of a lift with a light inextensible string. If the lift moves upwards with an acceleration of 2 meters per second squared, calculate the magnitude of the tension in the string. Here's what we have. We have the weight acting downwards. That weight acting downwards would be the weight acting downwards, and then we have the string, the tension, right? So the force in the string, let me call that Fs. This is called the free body diagram, where you just have the, try to put down all the forces acting on the body. Now, what's the weight going to be? Weight is equal to W is equal to mg, which would be 2 times 10, right? That gives you 20 newtons. So we have 20 newtons downward. We don't know what Fs is, but we also know that the general motion of the system, all right, at the end of the day, is upwards. The general motion of the system is upwards. So we use Newton's second law, F is equal to ma. All right, where this is net force, right? So the net force for this system, I'll call Fs positive, right? Upwards positive. So we're going to have net force would be Fs, that's, then minus 20 newtons, because the 20 newtons is facing downwards, all right, is equal to the mass of 2 kg times the acceleration of the system, which is 2 meters per second squared. That means that Fs would be equal to 4 plus 20. Fs is equal to 24 newtons, right? That's option B. That's option B. All right, question 5 says, a body of mass 5 kg moving with a velocity of 10 meters per second collides with a stationary object of mass 6 kg. If the two bodies stick together and move in the same direction after collision, find their common velocity. Right. So we're going to use law of conservation of linear momentum. Right. And that says that momentum before, so total momentum before total momentum before is equal to momentum after, total momentum after. That means that m1u1 plus m2u2 will be equal to m1v1 plus m2v2. All right, so u is initial velocity, where u is initial, v is final, that's velocity, right? And m is the mass. So mass 1, mass 2. All right, so let's drop this formula here and see what it comes to. We have the mass of the first one is 5 and at 10, so that will be 5 times 10, right? So mass of 5, m1, times velocity of 10, v1, u1 rather, plus the mass of the second one is 6, all right? So that's 6 times is stationary, so the velocity is 0. Now they're telling us that they both stick together and move together, right? That means that whatever this value is what this value is. All right, so we're going to say 5 times v, final velocity, plus 6 times v. All right, so they both have the same final velocity. So this would be 50 is equal to 11v. And so v would be 50 over 11, which is 4.55 meters per second. All right, 4.55 meters per second. That's option B. That's option B. A body of mass 8 kg moving with a speed of 30 meters per second is brought to rest in 2.5 seconds by a constant retarding force. Calculate the magnitude of this force. All right, so we're going to use the formula F is equal to mv minus mu over t. All right, so what's F is unknown. My mass is 8 kg. My final velocity is 0 because it was brought to a rest, right? So my final velocity is 0. My initial velocity is 2.5. I'm sorry, my initial velocity is 30 rather. Sorry, time is 2.5, yeah? So my initial velocity is 30 meters per second. And then my time is 2.5 seconds. Okay, so we'll just plug in. F would be equal to 8 times 0 minus 8 times 30 over 2.5. So F would be equal to 240 minus 240 over 2.5. Right, so minus 240 over 2.5. So that gives me 96. 96 newtons minus 96. All right, but since they asked us for just the magnitude, we can just take 96. All right, so it's also very okay to have used F is equal to ma. All right, and then we can just solve for A using equations of motion, right? So we can solve for A using B is equal to U plus AT. You plug in, you get your A, and you plug back in, and you get the same answer, right? So you can try that out also. All right, so both of them are very good options. Okay, so the answer is B. Question 7 says, the body of mass m moving with a velocity u collides with the stationary body of m2 and both move with a common velocity v. Okay, so I think this is supposed to be m1 actually, because looking at the option, right? So m1u1, right? Yes, moving the common velocity v. Good. So if linear momentum is conserved, which of the following expressions correctly represents v? So we can sketch out the formula for we can write out the formula for the relationship. Normally that will be initial momentum, that's m1u1 plus m2u2, right? That's the total initial momentum, is equal to m1v1 plus what? m2v2. All right, but then because v1 and v2 are the same, because it moves with a singular velocity, we could actually just write this as v and v. All right, we could actually just write this as v and v because they're both the same, and which can simplify this to m1u1 plus m2u2 is equal to m1 plus m2 times v. So we can factor out v like that. All right, what else do we have to simplify this? We are told that the second body is stationary initially. And if it's stationary, that means that the initial velocity is 0. So we can deduce that the u2 is equal to 0. All right, so this will just mean m1u1, because all of this becomes 0, right? Because 0 times m2 is 0, is equal to m1 plus m2 times v. And at this point, you can just divide both sides by m1 plus m2. All right, so that gives us the answer B, right? m1u1 m1u is equal to. Okay, next question. Question 8 says, a body of mass 4.2 kg moving with a velocity of 10 meters per second due east hits a stationary body of 2.5 kg. If they stick together after collision and move with a velocity of v due east, calculate the value of v. Okay, so we have momentum will be conserved, right? So we're going to have m1u1 plus m2u2, so this total initial momentum from both bodies must equal m1v1 plus what? m2v2. So this is the basic law, right, of linear momentum being conserved before and after. All right, but then we know that v1 and v2 are the same, right? So I mean, nothing stops me from going on ahead and just replacing that with v. So that will simplify my equation too. m1u1 plus m2u2 is equal to m1 plus m2 times v. All right, so at this point, we can plug in. Carefully though, what is the mass of body 1? That's 4.2 kg. What's the velocity of body 1? That's 10. All right, so we're taking east as positive. So anything that goes west, we take it as negative. All right, plus the mass of body 2 is 2.8, but the initial velocity, we are told, is stationary. So that's 0. So the second body initially was, just stays 0. All right, and it's going to be equal to m1 plus m2. That will be 4.2 plus 2.8 times the final velocity. In solving this cancels out, so we just have 42 is equal to 4.2 plus 2.8 would give me 7. And if I divide both sides by 7, I'll get my velocity as 6 meters per second. That's option A. So again, it's just the basic law of conservation of linear momentum, and then you're careful enough to substitute in nicely, looking out for what was stationary and the fact that they both moved with the same final velocity. So that just makes life easier. All right, next one, question 9 says, a car of mass 800 kg moves from rest on a horizontal track and travels 60 meters in 20 seconds with uniform acceleration. Assuming that there were no frictional forces, calculate the accelerating force. Calculate the accelerating force. Okay, so accelerating force, that force will be equal to F is equal to ma, mass times acceleration. All right, we have the mass at 800. We are looking for the force. And we also don't have acceleration, but we can solve for acceleration, right? Using our trusty equations of motion. So let's see what we can find. U is 0 because it starts from rest. The final velocity is unknown. They didn't give us that, and I don't think we need that anyway. So let me take that out. But they gave us S. All right, it covered 60 meters. That's your distance. We have T as 20 seconds. And okay, we're not given acceleration. Okay, so we can solve for acceleration. The formula that captures this for is, I believe, S is equal to ut plus half at squared. So I would say this, right, that if you don't know your equations of uniformly accelerated motion, then I mean that's like the basics of everything. So you need to go learn them. There are 4 of them. They're not hard to memorize. There is V is equal to U plus 8C. There is V squared is equal to U squared plus 2AS. There is S is equal to UT plus half AT squared. And there is S is equal to V plus U over 2 times T. Now, if you learn these formulas, or want to be better way to explain it, right, you feel powerful. You feel powerful because there are a lot of problems that you'll be able to solve, by, I mean, you might have been stuck, then you just, oh, wait, I can drop this, right? Actually, anything within kinetics, mechanics, right, which makes up most of book 1. All right, so I'm just saying, you need to learn the formulas and how to apply them. All right, so let's substitute. So we have S, that's 60, is equal to U is 0 times 20 plus half times A times 20 squared. So this is 60 is equal to, this will just cancel out. So this will be 400 A over 2. So 60 is equal to, this will be 200 A. So A by itself would be 60 over 200, which I think we can simplify to 3 out of 10. All right, so 3 out of 10. So that means that my acceleration here is 3 out of 10 meters per second squared. So I come back to this, F is equal to ME, I'll just have F is equal to 800 by 3 out of 10. That will give me 240 newtons. All right, 140 newtons. That's option C. All right, question 10. A force acting on a body causes a change in the momentum of the body from 12 kg per second to 16 kg per second in 0.2 seconds. Calculate the magnitude of the force. All right, so for this, we're going to have to use the equation, right? The impulse is right on equal to change in momentum. All right, impulse is given by F times T. And that's going to be equal to change in momentum, that's final momentum and initial momentum, right? That's mass times final velocity minus mass times initial velocity. So from this point, it's just plugging in. So F is unknown, right? So F times 0.2 is equal to mv. All right, so mv together, right, is this mass. Look at the units, mass and velocity, right? So it's together. So this 12 minus, and then sorry, mv is actually the later one, sorry. So that's 16. That'll be 16 minus 12. All right, so this is the final momentum, initial momentum. So this would be 0.2 times F is equal to 4. So F would be equal to 4 divided by 0.2, which is same thing as 4 times 5, which is 20. All right, so that's 20 newtons. So that's 20 newtons. That's option A. All right. Question 11. A force acting on the body causes a change in the momentum of the body from 12 kg/meters per second to 16 kg/meters per second in 0.25 seconds. Calculate the magnitude of the impulse. Right, so impulse is just giving us change in momentum, right? That's final momentum minus initial momentum. So this is just going to be, final momentum is 16. All right, and you can see momentum because it's mv, right? Mass and then velocity together, right? So 16 minus 4, and minus 12 rather, right? The initial momentum is 12. All right, so that's impulse is 4 Newton seconds. All right, it's 4 Newton seconds. So basically, this information is useless. All right, and I believe it was put in there to throw you off, just in case because if you see this, then tendency is that you probably go about calculating the force, right, introducing ft and then dividing both sides by t, and then you'll be wrong. So the correct answer is actually 4 Newton seconds. That's option B. 4 Newton seconds. That's option B. All right, a force acts on the body for 0.5 seconds. A force acts on the body for 0.5 seconds, changing its momentum from 16 kg meters per second to 12 kg meters per second. Calculate the magnitude of the force. All right, so we have impulse is equal to change in momentum. All right, so impulse is F times change in t, and that's equal to mv minus mu. All right, so we can substitute in. We're looking for F, so F times your time is 0.5. Okay, so the duration of the time is 0.5 is equal to mv. So mv is final momentum, right? So if you notice the way they gave this to us as mass times mass and velocity together, right? That's 21. All right, so the final is 21 minus the initial. Again, they gave us the initial mass times velocity together. Look at the units. All right, so that's 16. So 0.5 F is equal to 5. So F is equal to 10 newtons. All right, F is equal to 10 newtons. A. Okay, 13. A girl stands on a scale in a lift. If the reading on the scale is less than a weight, then the lift is moving. All right, so we need to consider all of this, right? So it has to be acceleration, because only acceleration will mess with the weight, right? So it has to be either upwards with uniform acceleration or downwards with uniform acceleration. Uniform speed will just mean like there's no change in her, there'll be no change in her weight, right? Because it will affect the net force. Okay, so the first thing you need to know is that your scale, all right, when you have a scale and someone is standing on it, all right, and someone is standing on your scale, right? Forgive my drawing. All right, this scale here is reading the reaction force. So this scale is reading the reaction force. Is reading the normal force it is pushing back up with. So if this is the scale and you're standing on it, you'll be applying a weight downwards, all right? And by Newton's third law of motion, all right, and also Newton's first law, all right, is that there would also have to be an upward force. All right, there would also have to be an upward force balancing out the person's weight. So is this upward force the normal or the reaction, which is a reaction force that the scale reads, not the weight of the person? So once you know that, you can now begin to actually analyze. So let's discuss. The person is here and the person is standing on it, and the person's weight is acting downwards. Let me put it that way. So there's a weight acting downwards, mg, and the person's and there's a reaction force upwards. Now the net motion of everything, right? Everything, the entire system is actually moving. So let's assume it's moving upwards. Then we can now discuss. So that would mean that means you have an acceleration upwards. Sorry, it's accelerating upwards, right? So I'm going to say the net force would be r minus mg, right? If I take r as positive, right? So r minus mg is equal to mass times the acceleration. So that means that r minus mg, r is equal to ma plus mg. So that means that r will be equal to m bracket a plus g. All All right, so when it's moving upwards, this is the formula you have for your reaction, which means that what it would measure would be greater. See, because your acceleration is now a plus g. What you would measure will be greater because your acceleration is now a plus g. So that means that for this one, the scale will read more. Scale will read more than weight. That's when it's accelerating upwards. Now, for when it's accelerating downwards, all right. So let's do it again. When it's accelerating downwards, I'm going to have r upwards minus mg. So remember, now it's accelerating downwards, right? R minus mg. My acceleration is now downwards. So that means it's going to be equal to m times minus a, because a is downwards. All right. So that means r would be equal to mg minus ma, or r will be equal to m bracket g minus a. So when it's acting downwards, you have less on the scale, because see, your acceleration is reduced, right? The acceleration that you use to calculate the reaction force is reduced. So it's an idea that you need to practice, right? So you might need to watch this a few times to get it. It's not difficult, but you need to practice it, to hold on to it. So even if they ask you what is the weight of the reading on the scale, and all of that, right? It's the exact same process. Just draw the system, put the acceleration if it's downwards or upwards, and just set it up. All right. So you can try it a couple of times to make sure that you actually understand. But once you can do this, you can answer any question on, a elevator problem, moving up, moving down, accelerating up, accelerating down. Now remember that if it's going with uniform speed, acceleration is 0, which means that your reaction will just be equal to mg. So there will be no change. That's fine. All right. So whether it's moving upwards with uniform speed or downwards with uniform speed, acceleration will be 0, and your reaction force will just be mg. Okay. So you want to, again, don't just watch this, get a paper and biro and try it out yourself, right? To ensure that you actually do understand it. So the correct answer to this, since the scale is reading less than our weight, we have to say that the object is accelerating downwards. Right? Is accelerating downwards. All right, 14. Right, question 14. A pellet of mass 0.5 kg is fired at the speed of 200 meters per second into a lead block of mass 0.95 kg at rest. Given that the block moves after the impact, determine its kinetic energy. Okay, so we're supposed to find the kinetic energy of the block, right? And that's given by half mv squared, all right, for the block, that is. Now, we are talking about after the collision has already happened, right? And it's safe to assume that the lead block is now, the lead bullet is now inside the lead block. So the mass would be the combination of both of them, right? The combination of the bullet and the block. So the mass would be 0.95 plus 0.05, which is 1 kg. All right, and then our velocity is what we need to find, because once we have our velocity, we can calculate the kinetic energy. So how do we get the velocity? We have to use the law of conservation of linear momentum. Conservation of linear momentum. All right, which states that total initial momentum would be equal to total final momentum. That's say m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. All right, so what's m1? m1 is 0.05, and then the initial velocity of the bullet, right, is 200 plus m2 is 0.95, and the initial velocity of that is 0. Now, if you look here, you would notice that on the other side, right, afterwards, you would notice that the final velocities will be the same because they are moving together. So I'll just call both of them v. Okay, I mean, you can do that, right? So I'll have m1, that 0.05 v plus 0.95 v. Okay, so just a bit of calculation now to get my value for V. This cancels out because 0 times 0.95 is 0, and 0.05 times 200 is 10. That would be equal to 1V. Okay, so basically V is equal to 1. Now I can come back here and solve for my kinetic energy using half mv squared. That would be equal to 1 over 2 times what's my m? 1 times what's my v? 10. All right, so we got v as 10 for the system. All right, so 10 squared. So at the end of the day, we would have that equal 100 over 2, which is 50 joules. 50 joules. So question 14 is C. All right, question 15. A moving body of mass 25 kg undergoes a uniform retardation of 20 meters per second. Calculate the magnitude of the retarding force. So this is Newton's second law. All right, that's F is equal to ma. That will just be equal to 25, right? The mass times the deceleration, that's minus 20. All right, so just ma. So F would be equal to minus 500 newtons. All right, but they're asking us for just the magnitude, right? So that means we're not taking into account the sign, just the scalar component, which is just 500 newtons. So that's D for question 15. So let's take on 16. 16 says a moving car of mass 800 kg experiences a frictional force of 200 newtons. If it accelerates with 2 meters per second squared, calculate the magnitude of the force applied to the car. All right, so we have Newton's second law states that net force, all right, so net force is equal to mass times acceleration. And in this case, my net force would be the force on the car. I mean, so you have a car. All right, you have a car, and of course, the engines of that car, by burning up gasoline, is applying, some force to move it forward. So F, right? So that's the force on the car. So let's say FC. And then, of course, the road would always do what it would do, right? It would have some friction backwards. So we can call that FF, right? Frictional force. So the net force would be, that would cause the acceleration would be FC minus FF. All right, would be mass. So that would be 800 times 2. All right, so I can even plug in my FF, right? So that would be FC minus 200 would be 800 times 2. So FC would be 1,600 plus 200. FC would be 1,800 newtons. All right, so that's the force on the car, or the force of the car is 1,800 newtons. So it needs 200 newtons to overcome the friction, and then the other 1,600 to produce 2 meters per second squared acceleration on the 800 kilogram car. That's option C. Right, question 17 says a net force of 15 newtons acts on the body of 3 kg for 5 seconds. Calculate the change in speed of the body. Okay. So for this, we're going to do we can use impulse, right? Impulse is equal to change in momentum. All right, so impulse, so that's Ft, is equal to change in momentum will be mv minus mu, m bracket v minus u. All right, so that's Ft. Now this v minus u that we have here, right? Sorry, I thought that was the highlighter. Sorry, let me try that. So this v minus u that we have here, that is the change in speed. All right, that's the change in speed, and that's what we're actually asked to find. So we'll substitute everything in and solve for v minus u. 15 times 5, sorry, let me get that. So that's 15 times 5 is equal to the mass 3 times, well, whatever V minus U is. So that means that V minus U, which is what we need, is going to be 75 over 3. So that's 25. So the change in speed, right, is 25 meters per second. That's option A. 18. A net force of magnitude 0.6 newtons acts on the body of mass 40 grams initially at rest. Calculate the magnitude of the resulting acceleration. All right. So we have F is equal to ma. That's Newton's second law, right? Force, net force, is equal to mass times acceleration. Our F is 0.6. Our mass is 40 grams, all right, which is, well, 40 over 1,000 in kilograms, which is 0.04, I believe. Okay, so 0.04 kg, and we are looking for our acceleration. So we just substitute. We have 0.6 is equal to the mass. Is equal to the mass. The mass is 0.04 times A. 0.04 A. So A would be 0.6 divided by 0.04. Let me do that here. 0.6 divided by 0.04. We can multiply top and bottom by 100, right? That gives 60 over 4. Okay, so that's 15. So my acceleration is A is 15 meters per second squared. So there's an issue here. Sorry, it should be per second squared. That's the unit of acceleration, so I'll change that. Okay, I hope that's fine though. So we just used the regular formula, but we had to change the mass to kilograms, all right, by dividing by 1,000. Okay, so 19. For 19, we have the resultant force of 15 newtons. The resultant force of 15 newtons acts on the body of mass 250 grams. Calculate the magnitude of the acceleration. All right, so it's basically F is equal to ma. Net force is equal to mass times acceleration. This is Newton's second law. My net force is 15 newtons. All right, my mass is 250 grams. Hold up. So the unit is kg, right? So that'll be 250 grams to kg. We have to divide by 1,000, all right, to get it to kg. So that would be 0.25. Okay, good. So 0.25 kg times acceleration times A. So our A would be 15 divided by 0.25, which is same as 15 times 4, which is 60 meters per second squared. So the answer is C. Okay, so we just used F is equal to ma, and then we had to change the mass to the SI unit of kilograms by dividing by 1,000. Okay. 20. 20 says a spring balance which is suspended from the roof of a lift carries a mass of 1 kg at its free end. If the lift accelerates upwards at 2.5 meters per second squared, determine the reading on the spring balance. Okay, so the reading on the spring balance is when you stand on a scale or a spring balance, it doesn't read, your spring balance will not read the weight per se. It would read the reaction force. So if you stand on this, for instance, on the scale, let's use a scale, right? If you stand on the scale, you have your weight downwards, all right? But by Newton's first law, all right, and also third law, but by Newton's first law more accurately, the fact that you're not falling through, the fact that you're stable is only because the scale is also providing an upward push. That's the only reason why, right? So you're pushing down, but the scale is also providing an upward push. All right. So and this reaction force is what the scale reads. The scale reads how much am I pushing you back up with. That means that in several systems, your scale will not read your actual weight. For instance, if you are on an incline, if the scale was on an incline, or if the space you're in is accelerating, anything that will alter the reaction force would alter the reading on the scale. All right. So, but in this case, you are in a lift and there's a mass of 1 kg. All right. So there's a mass of 1 kg. So let me just draw it this way. So we have a mass of 1 kg. What's the force? The weight is mg, right? So that will be 1 times 10, which is 10 newtons. So this has a weight of 10 newtons downwards. But then what's the reaction? All right. What's the reaction? Which is what the scale will read. That's R. We do not know. But the entire system, all right, the entire system is accelerating. The entire system is accelerating upwards at 2.5 meters per second. So there's an upward acceleration at 2.5 meters per second. And we'll call that positive, okay? Because it's upwards. All right, so let's do the calculation here. Newton's second law. We say net force is equal to the mass times the acceleration. All right, so what's the net force? I'm going to call everything upwards positive and everything downwards negative. So that will be R minus 10, right, because it's downwards, is equal to the mass 1 times acceleration. Now this acceleration is upwards, right? So times 2.5. That means that R minus 10 is equal to 2.5. So R will be equal to 2.5 plus 10. So R would be 12.5 newtons. 12.5 newtons. That's option C. Okay. 21. A stationary object of mass 4 kg is set in motion by a net force of 50 newtons. If the object attains its speed of 5 meters per second in time, calculate the value of time. So calculate how long it took it to achieve. I think that's what it means. Okay. So we can use Newton's law that says net force is equal to mass times acceleration. So we have 50 will be equal to 4 kg times the acceleration, which we do not know. That means that the acceleration is 50 over 4, which is 12.5. Sorry, 12.5 meters per second squared. Okay, so we have A as 12.5 meters per second squared. We have your U as 0, okay, because we are told that it is set in motion, right? So you assume that it was stationary. Oh, it was even written that was stationary. Okay, good. So your U is 0 meters per second. Your final velocity is 5 meters per second, and we're looking for how long. Okay, so the equation of motion that fits into this is the one that says that V is equal to U plus 8t. 5 is equal to 0 plus 12.5 by t. Right, so 5 is equal to 12.5t. Divide both sides by 12.5. You would have t as 5 divided 12.5. You would have t as 0.4 seconds. Right, so 0.4 seconds. That's option A. All right. So we are going to use our equation of motion, of course, but we need the acceleration. So we had to go back and use F is equal to ma to find the acceleration first, and then we could now solve using our equation of motion for time. All right, that's question 21. 22 says, A trolley of mass 4 kg moving along a smooth horizontal platform with a speed of 1 meters per second collides perfectly with a stationary trolley of the same mass on the same platform. Calculate the total momentum of the two trolleys immediately after the collisions. Okay, good. So we are asked to calculate the momentum after, all right? But then they didn't give us the speed after. We don't know anything that happened after. But if you think about it really, right, the law of conservation of momentum states that. So the law of conservation of momentum states that initial momentum, let me say total initial momentum, right, in a closed system would always equal the what? Total final momentum. Right, so this is what we usually interpret. So the m1u1 plus m2u2 is equal to m1v1 plus m2v2 formula. But what we have here right now is we're just asked for the total momentum. So if they're asking you for this, why not just solve for this since they're equal? All right, so it's just going to be m1u1 plus m2u2. That's all you need. All right, to find, and that would be equal to the everything on the other side. So m1u1, that's 4 times 1 plus m2, 4, because say it's the same mass, right? But it's stationary, so times 0. So the answer is just 4, right? Because this cancels out. So the answer is just 4, that's C. All right. So 23. An 800 kg car moving at 80 kilometers per hour collides with a 1200 kg car moving at 40 kilometers per hour in the same direction. All right. If the cars stick together, calculate their common velocity. All right. So we're going to use conservation of linear momentum. So we're going to have m1u1 plus m2u2 is equal to m1v1 plus m2v2. All right, so total initial momentum would be total final momentum. All right, so that's and I guess we can work with kilometer per hour. All right, since that's what we have even in the option, so it should be fine. It will be fine. All right, so we're going to go m1 800 times u1 is 80 plus m2 1200 times u2 is 40. All right, so that's equal to m1, which is 800, times final velocity 1 plus m2 1200 times final velocity 2. But see, the cars stick together. All right, so I mean, if you think about it, that means that velocity 1 and velocity 2 are the same. Right, that's why we're asked to find their common velocity. So that means that this formula actually changes to just v. All right, you can just leave v for both of them because they are the same. So with that, we're able to simplify our algebra and call this 2000 v. 800 times 80 would give you 64,000 plus 1200 times 40 will give you 48,000. So 2000 V is equal to 64,000 plus 48,000. That is 112,000. We can divide both sides by 2,000 now because we're solving for V. So V would be just 56. All right, and units same as all others, right? Kilometers per hour. So kilometers per hour, that's option C. All right, so 24. An external force of magnitude 100 newtons acts on a mass of 0.15 kg for 0.03 seconds. All right, so for this question, we're going to use the formula that says that impulse is equal to change in momentum Impulse is equal to change in momentum. So what's my impulse? My impulse is Ft, and change in momentum is mv minus mu. All right. We are asked for the change in the speed. Okay, so we're basically asked for v minus u. So I mean, it makes sense to write this as m bracket v minus u. So we know we're just solving for, for that, right? Okay, so f is 100 times time is 0.03 is equal to your mass 0.15 times v minus u, which is what we're looking for. 100 times 0.03 is 3 is equal to 0.15 times v minus u. So we just divide both sides by 0.15 to get our v minus u. Right, so that's 3 divided by 0.15, which gives you 20. All right, so that means that v minus u is equal to 20. So here's the thing. We really don't know what the initial or final velocity was, right? We just know that the velocity would have changed by 20. Okay. 25. An inelastic collision takes place between balls of known masses. Just before the collision, one of the balls is moving with a known velocity, while the other is stationary. Which of the following physical quantities can be determined from the information given? All right, so let's talk about it. It's inelastic. All right, so if it's inelastic, that means that kinetic energy is not conserved. It's only conserved in elastic collisions. Right, so we can't find, so let me just take off this one. Right, so we have the known velocity initially, and we also know the velocity of the other one. Good, so we can find the total momentum of the two balls after collision is correct. Why? Because total momentum after collision will be the same as initial momentum, right? And we know the masses and we know the velocities of both of them. So we can find the total momentum, just get the initial momentum and you have the total momentum. All right. So and you have the total momentum after collision, right? If you find the initial, you have the final. So it's D. And 6. A body of mass 2 kg is moving with a velocity of 3 meters per second. Sorry, a body of mass 2 kg moving with a velocity of 3 meters per second collides head-on with another object of mass 1 kg moving in the opposite direction with a velocity of 4 meters per second. If the objects stick together after collision, calculate their common speed. All right, so we have we're going to use the law of conservation of linear momentum. So mv, so we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. Okay, so we know m represents mass, right? So mass 1, mass 2. U represents initial velocity, and then v represents final velocity. So what's my m1? m1 is 2 for the first one, and the velocity is 3. So 2 times 3 plus m2 is 1, and the velocity of the second one, so we are told is moving the opposite direction. Remember, velocity is a vector, right? So that will make this minus 4. Opposite direction minus 4. All right, so this would be equal to m1. Sorry, I can write m1 now. So m1 is 2. So 2v1 plus what? 1v2. All right, but if you also look at it, we are told that they stick together after the collision and they have a common speed. That means that the final velocities are the same. So we can just represent them as v, right? Since they are the same, so we have 3v is equal to, so I'm writing backwards now. This is going to be 6. 2 times 3 is 6 minus 4. So 3v is 2. So if I divide both sides by 3, I will get, sorry. So I have 3v is equal to 2, so v would be equal to 2 over 3, which is 0.667 meters per second, right? Or 0.67, that's A. All right. 27. An object of mass 5 kg moves with a velocity of 10 meters per second. Calculate the momentum. All right, so momentum, formula for momentum, P is equal to mass times velocity. Okay, so momentum P would just be mass, that's 5, times velocity 10, which gives you 50. All right, 50 kilogram meter per second. All right, so that's option D. All right, 28. 4 identical trolleys are loaded with different masses and move along a straight road at the same speed. Which of the trolleys has the greatest inertia? Okay, what is inertia? Inertia is the, well, resistance to change your state of motion. All right, so it can just be said to be your stubbornness, right? So stubbornness to force application. All right, so stubbornness to application of force. So anything that you need to do a lot of before it bulges, right? So it has a high inertia, and you know that, just by intuition, right? You know that the more the mass, the heavier something is, the less is likely to bulge. All right, so again, that's now Newton's second law. All right, that your force is, well, your acceleration is inverse proportional to mass. All right, so if I have F is equal to ma, all right, then that means that A is equal to F over m. And if F is constant and I'm just monitoring the system, I can say A is proportional to what? 1 over m. So they're inverse. So that means that the more the mass, the less the acceleration. All right, so the more the mass, the more the resistance to change. All right, so we have to just pick out, all we have to do is just pick out the one with the highest mass, and that's option A. So that's, the one with the highest mass is the heaviest and it has the greatest inertia. All right, it's 9. From Newton's first law of motion, A, once a body remains at rest, no force acts on it. That's not true. A is wrong because something could be maybe resting on the table, right, and exerting a force of 10 newtons downwards. Of course, it has a weight, right? But the only reason it's not moving is because there's another force acting on it, pushing it upwards. So what you would say is that there are no unbalanced forces, because this force is now balanced. So if I have 10 newtons down and I have 10 newtons up as a reaction force, then it's going to stay on the table, right? It's not going to fall through, right? It's just going to stay on the table. So it's at rest, but there are actually forces acting on it. So this is wrong. If they had said once the body remains at rest, no unbalanced force, would have taken that. All right, B says a body's inertia is its weight. That's also not true. Now, a body's inertia depends on its weight. It's proportional to its weight, but it's not exactly its weight. All right, so B is wrong. A body can only undergo translational motion. I don't even know where they got that from. That just doesn't make any sense, right? You can undergo translational, random, oscillatory, whatever kind of motion you want to undergo. D says the net force acting on the body in uniform linear motion is 0. So this is correct. All right. So if the motion is uniform, that means it's at constant speed. All right, constant speed, which also means no acceleration. So the correct answer here is D. D is the correct answer. All right. Number 30 says fuel was consumed at the steady rate of 5 times 10 raised to the power of minus 2. All right, so that's 0.05 kg per second in a rocket engine and ejected as a gas with a speed of 4,000 meters per second. All right, determine the thrust on the rocket. All right, determine the thrust on the rocket. So for this question, I'm going to use dimensional analysis. All right, my guess already is to just multiply them because all their units are the same, and I can see that the seconds will cancel out. The second will become raised to the power of minus 2. So already I can see that this will give me actually newtons. All right, just by multiplying. Right. So because there is no formula that gives you mass per second times speed, right? Sorry, kilogram per second times speed, right? Then times meters per second. I've never seen a formula like that. But just by going by the dimensional analysis, you can see that multiplying both of them would give you the units you have in the options, right? So what's the dimensional analysis for force? So let me do that first so we know where we're going to, because this is Newton, right? Force is mass times acceleration. That would be kilogram for mass times meters, that's L, meters per second squared. Right? So this is this is supposed to be M, right? For dimensional analysis. So this is MLT to the power of minus 2. Right? So MLT to the power of minus 2. This is for force. Now let's take this on. Mass per second. This is M over T times meters per second. This is L over T. And guess what we have? We have MLT to the power of minus 2. So obviously by multiplying these two, I'm going to get the unit that I want. All right. So that we have in the options. So let's do that. So that'll be 0.05, right? 0.05 times 4,000. That gives me 200 newtons D. 200 newtons D. Okay. The time rate of change of momentum is force. All right. So it's very tricky because some people might go with impulse, but it's actually force. And why is that? Now, if they just said change of momentum, that is mv minus mu. So you're likely to just go, this is ft, right? If you change of momentum, I'll take impulse as an answer. But because it's rate of change, that means that you're saying that change of momentum over time. All right, and if you do that, you end up with just force. So the correct answer is C. All right, 32. If no net force acts on an object, the object remains in a state of rest or constant speed in a straight line. The above statement is Newton's first law of motion. All right, first law of motion. All right, an object at rest would remain at rest unless acted upon by, an unbalanced force. So that's Newton's first law. All right, 33. In a collision between two objects, kinetic energy is conserved only if the collision is elastic. All right, so in elastic collision, kinetic energy is conserved. In inelastic collision, kinetic energy is not conserved. All right, and the reason why it's not conserved in inelastic collision is because a considerable amount of the energy is lost to deformation, because the two objects they'll crash into each other, right? So they are not elastic in nature, so they will not just bounce and go back and all of that. They'll crash into each other. So a lot of energy will be lost in the process of one or both of them being deformed. All right, so the correct option is option B. All right, if the collision is elastic, then you can also apply the formula for conservation of kinetic energy. Step 4. In elastic collision, momentum is conserved, yes, as well as kinetic energy. So it's the same as the last question, right? In elastic collision, momentum and kinetic energy are conserved. In an inelastic collision, only momentum is conserved. All right, 35 says, the engine of a car provides a forward force of 1,240 newtons. The total resistive force on the car is 800 newtons. If the mass of the car is 1,200 newtons, determine the distance the car has to travel from rest before acquiring a speed of 4 meters per second. Okay, so the end point is we're asked to find distance. All right, and that's S. So we need to find S. We have U as 0 from rest. We have V as 4 meters per second, final velocity. And we need acceleration. I mean, because we can get acceleration from what we have up there, right? So we can use Newton's second law that says net force is equal to the mass times acceleration. So we have a car. And there's a forward force of 1,240. So the car is pushing itself forward with 1,240. And then there's a resistive force, all right? So that could be air resistance and friction or whatever, but the total of all of them is 800 newtons. So the net force, would be 1,240 minus 800, all right? Because the force is forward, 800 is backwards. So what is mass? Mass is 1,220 times A. We don't know what A is. So we would have, this would give me 440 is equal to 1,220 A. I divide both sides by 1,220. I'll get A as A is 0.361. So 0.361 meters per second squared. So I'll drop that here, 0.361 meters per second squared. So I have to move this over here, right? Let me just write out my variables. We have U as 0. We have B as 4 meters per second. We have A as 0.361 meters per second. And we are looking for S. So the equation of motion that works with all of this, right, is V squared is equal to U squared plus 2AS. So V squared is 4 squared is equal to 0 squared plus 2 times 0.361 times S. All right, so that means that 16 is equal to, that should be 0.722S. Let me just confirm, sorry, 0.361 times 2. Yes, 0.722 times S. That means my S would just be to divide both sides by 0.722. So that gives me 22.16 meters, rather, right? 22.16 meters. That's C, 22.2 meters. All right, so we asked to find distance. An equation of motion would have, but we did not have the acceleration. So we solved for the acceleration using the Newton's second law, found the net force as 440, and then we're able to solve for acceleration. Once we had that done, we went back and plugged that back in and we were good. All right, so 36. The following statement are observations made about a towing vehicle and a bus that is being towed. The force exerted on the force by the towing vehicle is of the same magnitude as the force that the bus exerts on the road. We have no proof of that. Newton's third law, which is what I think is being portrayed here, is that the force of A on B, all right, so the force of A on B must be the same as the force of B on A. All right, so let's read through. The force exerted on the bus by the towing vehicle is the same magnitude as the force exerted on the towing vehicle by the bus. I think the second one is a winner. The towing vehicle exerts a force on the bus greater than the force exerted by the bus on the towing vehicle. Wrong. The towing vehicle exerts a force on the bus that is the same as the force the road exerts on the towing vehicle. No. All right, so it's A on B is the same thing as B on A. All right, so this is Newton's third law. A on B is same, right? Is same as B on A. That's that. That's II. It's 7. The mass and weight of a body on Earth are 8 kg and 18 newtons respectively. Determine the mass and weight of the body respectively on the planet when the pull of gravity is 1/8 that of the Earth. Okay, good. So your mass does not change, right? Mass is defined as the amount of matter, right? It's a way of quantifying the amount of matter a body contains. Okay, so this is your mass, all right? And just because you left to a different planet will not change how much matter your body contains. But then the ability of the planetary body to pull you towards itself, which is weight, all right, that would depend on, well, a number of factors, right? But that would change, all right? So weight depends on the planet, all right? So we are told that so the first thing is we can eliminate the options that have different masses, right? Those are wrong. All right, now the mass, so on planet A or planet Earth, sorry, the mass is 8 kg. Your acceleration, is 10, all right? 10 meters per second squared. You can even divide, mass FA, right? W is equal to mg, or F is equal to me for this to get the acceleration. And your weight is 18 newtons. Now on planet B, your mass is still 8 kg. Your acceleration is now 1/8 of that on the Earth. So that would be 10/8, right? So 1/8 of 10, right? So that's 10/8. That's 5 out of 4. So 5 out of 4 meters per second squared. All right. So what's now the weight? So we can still do weight is equal to mg, which would equal, sorry, let me call this 2g, right? So which would equal 8 times 5/4. All right, which is just 10. So 10 newtons. All right, so it's 10 newtons. The correct answer is B. All right, so I went all around to explain. You could have just said, force is directly proportional to gravity. So if gravity reduces by 8, the force reduces by 8. So that'll be 80/8 by a factor of 8, 80 divided by 8, which gives you 10. You'd have been right. Yeah, you'd have been right either way. So I just went the long route so that you can see the relationship between mass and gravity and weight. So you can, try to implement this again and see how you're able to manage this. All right, that's 37. 38. The mass of the load is doubled while the force acting on it is halved. The resulting acceleration of the load is good. Okay, so this is a skill that I try to get, basically just manipulating variables. So you need to practice this because they could ask this kind of question on any topic, right? They could ask this kind of question on any topic, any topic that they like. They could ask it. As long as there's a formula, they can say, let's say we're using kinetic energy, for instance, half mv squared, and they will say, the mass is doubled and the velocity is halved. So what happens to kinetic energy? All right. So but is the method more than the solution as it were. So just let's do this together. So the formula that relates all of them is F is equal to ma, but we want to monitor the acceleration, right? So it's best to make acceleration subject of the formula. So I'm going to say A is equal to F over m. In fact, I'm going to say A1, all right, for the first scenario, because we're trying to monitor what happened in the second scenario, right? Now so this is A1. Now for A2, what is F? F is halved, right? So we're dealing with F over 2 divided by, all right, instead of F over m, and then the mass is doubled, right? So we have 2m under in place of m. All right, now this is just algebra. We can just say F over 2 divided by 2m is, I write it out this way whenever I have multiple fractions, right? Maybe one fraction or whatever, so that I'm able to see clearly. So this is F over 2 divided by 2m. This will be F over 2 times 1 over 2m, right? So times 1 over 2m. So this is just basically F over 4m. So you find out that A2 is equal to F over 4m, of which I can easily factor out 1 over 4 now and just leave my F over m inside, all right, for A2, which implies that A2 is equal to 1 over 4 of what? F over m is A1, 1 over 4 A1. So that means that in doing this, the acceleration has become 1/4 or a quarter of what it was. All right, in doing this, the acceleration has become a quarter of what it was. All right, that's 38. 39. The property of a body to remain at rest or continue in uniform motion in a straight line is called inertia. Right, that's C. So inertia. So inertia is resistance to change in motion or rest. All right, inertia is what Newton's first law is predicated on. All right, so a body wants to stay at rest or continue doing whatever it was doing unless acted upon by an external force, and that external force has to be enough to overcome the inertia of that system, right? So that's option C for 39. Question 40. The tendency of a stationary body to continue to remain at rest when a force is applied to it is known as inertia. Sorry, let me clean out. So it's inertia, right? So inertia is the tendency of a body to just want to keep doing whatever it was doing, right? So it's on this idea that Newton's first law and second law were predicated. All right, the idea that inertia, so for you to change or alter the state of an object's motion, you must overcome its internal resistance to change in motion, and the name given to that is inertia. So that's D. Okay, 41. The tendency of a body to remain at rest when the force is applied to it is inertia. All right, so inertia is like a body's internal resistance to change in motion. Newton's first law states that a body will remain at rest or continue to move at a constant speed unless you apply an external force to it, right? So a body's insistence on not moving or not changing, what it's doing, the initial state of motion is called inertia. All right. So it's an internal property of the body. Friction is similar to inertia, but friction is external. Friction is when, from external factors, maybe from the road or from whatever, two objects trying to move one another. So it's external. But inertia is the an internal state of a body to not want to move, not want to change its state of motion. All right, so the correct option is C. Okay, two forces, 100 newtons and 6 newtons act on an object of mass 70 kg, as illustrated in the diagram below. Neglecting friction, calculate the acceleration of the object. This is Newton's second law, right? That states that summation F, or net force, all right, is equal to mass times acceleration. Okay, so we have our mass as 70 kg. What we need to find is our net force. All right. If you add up 160 just like that, you'll be wrong, right? You'll be wrong, and the reason why is because this 100 newtons, not all of it is actually useful in the horizontal motion, right? So there's just a component of it. There's a part of it that is useful, but not all of it, and we need to find that that component, right? The x component of this force. Now, thankfully, this follows the same principle as this follows the same principle as your regular right triangle SOHCAHTOA angle side relationship. So this is 45 degrees and 100 newtons, and we need to find the horizontal component, all right? Because this component, this part of it is what is useful. So x is your adjacent, right? So we have adjacent as x, you have your hypotenuse as 100, and you have your angle theta as 45 degrees. So we're going to go cos. It's cos that released three of them. So cos theta, cos 45 is equal to adjacent over hypotenuse is equal to x over 100. All right. So that would be x as 100 cos 45, which would give you 70.71. So the component of this 100 that is actually useful in this forward motion is 70.71 newtons. And these two together become your net force. All right. So my net force. So now my net force will be equal to 70.71 plus 60, which is 130.71. Now I can calculate my acceleration, right, by saying 130.71, now I'm using the formula, is equal to my mass 70 times acceleration. So that means acceleration will just be 130.71 over 70. 130.71 divided by 70. So that gives me A as 1.867 or 1.9 meters per second squared. That's option A. That's 42. 43. What change in velocity will be produced on a body of mass 4 kg if a constant force of 16 newtons acts on it for 2 seconds? All right, so for this, we're going to use impulse is equal to change in momentum. That's F times change in T. F times T is equal to change in momentum will be mv minus mu. When we look at this closely though, we just need m bracket v minus u. We can factor that out because what they are actually asking us for is v minus u. All right, is v minus u. Now we can substitute. That would be 16 times 2 is equal to 4 times v minus u. Now we can divide both sides by 4. So we have that v minus u is just 8, right? 8 meters per second. The interesting thing is that we don't know the original velocity. We don't know the final velocity, but we just know that the change in velocity that was produced by this is 8, right? So it went up by 8 meters per second. All right, question 44. When a lightweight body and a massive body are acted upon by the same force for the same period of time, which one would have more momentum? All right, so we have They both have the same impulse, basically, right? Because the force is acting for the same period of time. And we know that impulse is equal to change in momentum. Right? So that means that Ft would produce the same change in momentum in both of them. If I assume that they are both, they both have the same initial momentum, then that means that the both of them would have, both of them would remain the same. Yes, both of them will have the same momentum at the end of the whole thing, because basically it's impulse, right? They have the same impulse, so they will have the same change in momentum. So that means that if one of them had, the one with the lighter mass, like this one had a small mass, would definitely receive a higher velocity, but the one with the big mass would receive a smaller velocity. But at the end of the day, their momentum, when you multiply it, would be the same. All right, so the correct answer is D. Momenta of both bodies would be the same. Question 45. When the linear momentum of a body is constant, the net force acting on it is 0. All right, because if you think about it, F is equal to ma. That means that if F exists, all right, maybe F is 5 or 10 or whatever, then that means that you have an acceleration. If you have an acceleration, your velocity changes. And that means that your momentum would also change, because momentum is equal to F. We can even use, impulse and, or F is equal to M bracket V minus U over T, all right, to answer this. All right, so if there's any net force acting on it, then there'll be a change in momentum. In fact, Newton's second law can be explained by saying that that force is directly proportional to the change in momentum. Let me say there's a force, there'll be a change in momentum. Right, so the correct answer is that the net force has to be 0 if there is no change in momentum. 46. Which of the following are contact forces? Force of friction and force of tension, force of friction, magnetic force, force of reaction. So it's everything apart from 3. All right, everything apart from 3. So that's 1, 2, and 4. 1, 2, and 4. That's C. That's 46. 47. Which of the following is not a consequence of a force field? Which of the following is not a consequence of a force field? That's surface tension, because gravitational pull is a consequence of the of the Earth's gravitational field. Weight is a function of the Earth's gravitational field. In fact, weight and gravitational pull are the same thing, right? Magnetic force is a function of the magnetic field around the magnet. So it's only surface tension that is not a consequence of any force field. Which of the following quantities is not an example of force? Weight is a force, right? The unit is newtons. Weight is equal to mg, mass times acceleration. Tension is a force. Friction is also a force. So the correct answer is mass. Mass is just the amount of quantity a body contains, right? The amount of quantity a body contains, that's the mass. 49. Which of the following examples is not an example of a force? All right, so the weight is a force, right? Because it's basically the Earth's pull on the body, right? So it's mass times gravity. That's F is equal to ma. The unit is newton, so it's a force. Tension is also a force. It's just a force in the string, that's all. All right. Friction is a force also, right? Friction is a very major force. Is the reason why Newton's second law of motion seems to be a lie, because just about everything, first law of motion rather, seems to be a lie, because just about everything seems to want to stop as opposed to want to continue moving. And that's because there's friction everywhere. So friction is a force. The correct answer is mass. Mass is not a force. Mass is just a measure of the amount of matter an object contains, right? Is a measure of the amount of matter an object contains. So that's D. 50. Which of the following statements about a moving object is correct? Which of the following statements about a moving object is correct? When accelerating, the resultant force acting on it must be equal to 0. That's wrong. All right, because when accelerating, that's when you must even have a resultant force, right? And that's Newton's first law of motion. Acceleration must be caused by force. If there's no force, there's no acceleration. B, there must always be a non-zero resultant force acting on it. That's not true. An object can move without any unbalanced force. It's just that it won't be accelerating. It will be moving at a constant speed. So force causes acceleration. Force doesn't necessarily cause motion. Force causes acceleration. All right, so it causes a change in motion. So if something is moving at a constant speed, then there is no net force acting on it. All right, so 3, at steady velocity, air resistance must be equal to 0. No, that's wrong. At steady velocity, the resultant force acting on it must be equal to 0. That's true. All right, because force causes an acceleration. So if there is no acceleration, if it's moving at a steady speed, then the resultant force acting on it must be equal to 0. That's option D. 51. Which of the following statements about a moving particle is correct? Which of the following statements about a moving particle is correct? The rate of change of its momentum with time takes place in a direction that is opposite to that of its motion. No. The rate of change of its momentum is in the same direction as its motion. The particle freely falling covers equal distances in equal time intervals. That is not true. That's only true when the object has attained terminal velocity, right? But when the object is, regular free fall, no, it's accelerating. So it's speeding up. And in speeding up, that means it will begin to cover more time in, the same time interval. See, if the resultant force acting on the particle is greater than 0, then it is moving with a uniform velocity. That's false. That's false. Because resultant force, if it's not 0, then that means that it will be accelerating, to be causing it to change the dynamics of its motion, right? So it's either going to be speeding up, slowing down, or changing direction, right? So it won't be undergoing uniform velocity. That's in contradiction to Newton's first law. D is the correct answer. If the resultant force acting on the particle is 0, then it is in dynamic equilibrium. That means it will be undergoing uniform velocity. All right, so dynamic equilibrium really simply means that it is moving, but it is not changing, the dynamics of its motion. It's just, maintaining the state of motion, which is right in tandem with Newton's first law. So that's option D. 52. Which of the following statements about elastic collision is correct? Elastic collision, that's the statement that both kinetic energy and momentum would be conserved, right? In elastic collision, kinetic energy and momentum are both conserved. So you can use the formula. M1U1 plus M2U2, which is total initial momentum, right, is equal to M1V1 plus M2V2, this total final momentum, right? V for final velocity, U for initial velocity. All right, and you can also use half mu squared plus half mu1 squared plus half m2u2 squared is equal to half mv1 squared plus half m2v2 squared. So again, total kinetic energy after is equal to the total kinetic energy initial, and then total momentum after is total momentum initial. So you can use both formulas for elastic collision. So that's option B. 53. A body of mass 5 kg moving with a velocity of 30 meters per second due east is suddenly hit by another body and changes its velocity to 50 meters per second in the same direction. Calculate the magnitude of the impulse received. All right, so impulse is equal to change in momentum. That means that F times T is equal to mv minus mu. All right, but we had really just asked for impulse, right? So we can just calculate the change in momentum, right? So impulse would be So impulse will be mass, that's 5 times final velocity 50, minus mass 5 times initial velocity 30. So this would be 250 minus 150, which gives me 100 Newton seconds or kg meters per second. All right, so that's option D. Okay, so we've come to the end. Thank you.